Welcome to my project bazaar.com. Let me discuss about the project single tap equalization for fast OFDM signals under generic linear channels. Let me discuss about the abstract of the project. Orthogonal frequency division multiplexing is a method of encoding digital data on multiple carrier frequencies. Orthogonal frequency division multiplexing is a method of digital modulation in which a signal is split into several narrowband channels at different frequencies. A low complexity fast OFDM scheme is proposed, which enabled efficient single tap equalization for generic linear channels. The proposed technique is simpler and avoids net data rate loss compared with existing approach. The complexity and the performance of SCFDE system is comparable to that of OFDM while avoiding the above mentioned drawbacks associated with multi-carrier implementation. On the other hand, FDE does not represent an optimal solution to signal direction over ISA channels, and SC systems cannot certainly offer the same flexibility as OFDM in the management of bandwidth and energy resources, both in single user and multi-user communication. A major design challenge for high-speed broadband application is the time dispersive nature of the terrestrial radio channels. The effects of multipath propagation can be analyzed in the time domain or in the frequency domain. In the TD, we note that when the time spread introduced by the channel is larger than one symbol period, the inference among consecutive transmitted symbols, known as ISI, distorts the received signal. In the FD, if the communication bandwidth is larger than so-called coherence bandwidth of the channel, then distinct frequency components of the transmitted signal will undergo different attenuation, resulting in a distortion. Fast OFDM schemes which can efficiently compensate generic LTE channels without the symmetric constraint on the SCSCIR. Here DCT is replaced with DFT at the receiver. To reduce the data rate losses, DFT of double length, that is, n subcarriers are demultiplexed by the DFT on 2n point used. Zero padded is added. GA is added at the transmitter side. Zero padding that pads the guard interval with zeros. Proposed scheme achieves better performance under wireless frequency selective padding channels. Let me discuss about the flow diagram for our process. Here we design the fast OFDM blocks. OFDM systems have some advantages for mobile wireless transmission as signals are robust against frequency selective padding. For digital signal processing application, OFDM system has become inexpensive and available in consumer products. The intrinsic design of an OFDM system prevents inference among the carriers, also called subcarriers. Inserting a cyclic prefix before transmission can be avoided intersimple interference. This OFDM contrasts to ability to select the channel selectivity both in frequency and time. The optical fast OFDM has been proposed. In contrast to conventional OFDM, FOFDM uses half of the subcarrier spacing with a single dimensional signal modulation formats being used, such as M-array amplitude shift keying due to the increased intersymbol interference, that is ISI, between adjacent narrowband FOFDM subcarrier. Very recently, FOFDM has been effectively implemented experimentally in single mode fiber, that is SMF system, and the employing discrete cosine transform has been implemented for double side band signals, while for single side band signals the real to emittance symmetric property of fast Fourier transform or else the inverse fast Fourier transform as proposed. Due to limited bandwidth associated with multimode fibers, OFDM can be considered as an effective solution to combat optical model dispersion in MMF-based transmission links. Next, in the ADC, analog to digital converters have been considered as one of the most important devices for conventional OFDM systems, limiting the maximum achievable transmission performance, and therefore, in the same manner, ADC parameter also crucial factor for fast OFDM systems. Next, the simulation of FDE based ZF and MMSE has been performed. Frequency domain equalization applied to single carrier modulation solution. OFDM combined with time division duplexing using minimum mean square error frequency domain equalization has been reduced. The PAPR linear equalizer aims at minimizing the variance of the difference between the transmitted data and the signal at the equalizer output. A minimum mean square error estimator is an estimation method which minimizes the mean square error of the fitted values of the dependent variable, which is a common measure of the estimated quality. Next, in the DFE or else MLSE equalizer has been used. Channel equalizer are either linear or nonlinear. Nonlinear equalization is needed when the channel distortion is too severe for the linear equalizer to mitigate the channel impairments. An example of linear equalizer is a zero forcing equalizer, and as the name implies, it forces ISI to become zero for every symbol decision. The zero forcing equalizer enhances noise and results in performance degradation, and on the other hand, a minimizes mean square error or minimizes the error between the received signal and the transmitted symbol without enhancing the noise. Although the DFE based equalizer performs better than ZFE equalizer, its performance is not enough for channels with severe ISI. An obvious choice for channels with severe ISI is a non-linear equalizer. Finally, the comparison graph will be performed. That is, the comparison of SNR between fast OFDM schemes and FDE based schemes. This system has some advantages for mobile wireless communication, as channels are robust against frequency selective fading. The performance of the proposed tone based scheme is good high SNR and high. It increases the monotonously with increasing SNR, and with increasing the performance of the scheme was deteriorated as compared to its performance in AWGN. Let me discuss about the running procedure for our process. Select the main.m file in the current folder, right click the file and run for executing this process. This is the burst error from DFE, the burst error performance for MLSE. This is the BER graph for MMSE equalizer. Decision feedback equalizer and maximum likelihood sequence estimation performance are similar. It provided same BER rate, but in the system complexity for MLSE and is low compared with DFA. This process will take some time for executing. This is the BER response for our MMS equalizer with one simulation results and with two theory results. And this is the burst performance for MLS equalizer, and this is the bit error rate response for nonlinear equalizers, that is both DFA and MLSA. These both are achieves same bit error rate. And the system complexity response for DFE and MLSE equalizer. The X label denotes the iteration level, Y label denotes the system complexity. Here the MLSE achieve lower system complexity, and as the DFE achieve higher system complexity. This optimal equalizer is sensed with highest probability correctly detects the transmitted sequence is the MLSE. Thank you.